Hello, good morning. Today we are on the topic shear force and bending moment diagram. In this class, we try to draw the shear force and bending moment diagram for simply supported beam subjected to concentrated load at center and simply supported beam subjected to uniform distributed load entire the span of the beam. First, try to draw the shear force and bending moment diagram for concentrated load. A simply supported beam, a simply supported beam, a simply supported beam is subjected to a concentrated load. So it is a point load at center at center of the span of the beam. Span of the beam. Draw a simply supported beam. This simply supported beam is freely resting by the support and point load say W at center of the span the beam, point load W. Let me consider the length of the beam is L. Now we have to choose a point A, point B. Now find out the reaction. Find out the reaction. Reaction at point A, RA. Find out the reaction at point RA. Find out the reaction at point B, which is RB. Now how to find out the reaction? Consider at any point bending moment is 0. Obviously in case of simply supported beam, moment at a support is 0. So moment at point A is 0 and moment at point B also 0. Now let me consider taking moment about point A, either point A or point B is 0. Taking moment about point A is 0. Moment about point A is 0. So summation of moment at point, all the moment at point, moment of all the force, summation of moments of all the force at point A is equals to 0. Now find out the moment at point A. We can find out the moment at point A by reaction force RB and by the downward load W. So moment about point A, RB into total length perpendicular distance. So moment about point A by the reaction force is RB into L. RB into perpendicular distance total L, and this distance is L by 2, that is center of the span or center of the beam, L by 2. Now moment, this is the, we can consider if this negative, this is anti-clockwise moment, that means negative moment, negative, or either you can also consider positive, and by the load W load, this is the opposite reaction load, this is the load and this is the opposite reaction. By this load the moment at point A will be W into L by 2, which is positive, plus W into L by 2, that is equals to 0, because moment, we consider the moment about point A is equals to 0. This is the total moment about point A, and this is equals to 0. This is equal. Now find out the RB from this equation. So RB will be W into L divided by 2 into L, that means W by 2, which is upward direction, positive. This is upward direction. So we have to find out so we have find out the find out the RB, which is equals to W by 2. Similarly, RA equals to, sorry, this is the RB equals to W by 2. Similarly, we also calculate the RA. How to calculate the RA? Now, RA, reaction RA plus reaction RB is equals to total load applied on the beam, that is W. So RB, we know RB equals to W by 2. So here we have to find out the we can find out the RA equals to W minus RB. RA equals to W minus RB. You already find out the RB equals to W by 2. Put the value of RB. So W minus W by 2, which is equals to W by 2. It is also upward direction, positive. So RA equals to W by 2. Now find a shear force and bending moment diagram. Let me brief review of sign convention, shear force and bending moment diagram. Let me brief review. What is shear force, sign convention of shear force and bending moment diagram? Here you can see the sign convention for shear force. Sign convention for we consider a beam, simply supported beam, subjected to a point load at center C. We consider a section XX. In the left side section, the total resultant force is 500 Newton, which is upward direction, that means a positive shear force. And the right side section, in the right side section, total resultant force is 1000 Newton is acting downward, and the reaction is upward. That means the resultant force is 1000 minus 500, that means 500, which is downward. So in this case for simply supported beam, the shear force at a section will be considered positive when the resultant force to the left of the section is upward direction. The resultant force in the left side section is also upward direction. That means the positive shear force. In case of the right of the section is downward, obviously it should be downward. Similarly, the shear force at a section will be considered negative if the resultant force to the left of the section is downward. Always, if resultant force is upward direction, then positive. It means the left of the section, if the resultant force is downward direction in the left side section, that means the negative shear force. Or to the right of the section is upward. Always, if downward direction force is applied, resultant force is downward, then a positive shear force. If in the case of right side section, it always upward direction. Now find out the shear force and bending moment diagram. Now find out the shear force diagram. Let me draw again the simply supported beam. Simply supported beam RA is equals to W by 2 and RB is equals to W by 2 and load at center is W. This is L by 2 and total length is L. In the left side portion, the upward direction resultant force is upward direction. That means the left side section is positive shear force and right side section is negative shear force. So shear force at point A. Shear force at point A. Find out the shear force. Shear force. Shear force at point A is equals to positive what? Positive reaction at A, RA, which is equals to W by 2. Now shear force at point C. Shear force at point C, which is equals to shear force at point C, that means total force at point C. Total upward force at point C, what? Total upward force? Upward force W by 2, upward force W by 2 minus downward force W, so minus W by 2. And shear force at point B is equals to, in the right side section always negative, that is W minus reaction B, which is equals to minus W by 2. In this case, now draw the shear force diagram. Let me draw the shear force diagram. This is beam. Shear force at point A is equals to W by 2 is constant value, W by 2, and shear force at center is minus W by 2. It is constant value minus W by 2. Is it linear? No. It is constant value minus W by 2. And shear force at point B is equals to also minus W by 2. Now draw the shear force. This is also constant value, this is also constant value. We cannot draw in linear. It is not a linear equation. It is a constant value. Let me draw the diagram. So at point C, the total load is W. Yes, this is W by 2. So W plus W by 2, that means total load is W. It's consider its applied load. At point A, the shear force is W by 2, that is positive shear force, and in this zone the negative shear force. This is a shear force diagram for simply supported beam subjected to point load. Shear force diagram. Now find out the bending moment and draw the bending moment diagram. Then draw the bending moment diagram. Bending moment. Now find out the bending moment at point A and point B. Always we know bending moment for the simply supported beam is at the support point. At a support, the bending moment is 0. So we can write the bending moment at point A is equals to 0. Also bending moment at point B also equals to 0. Now what is the bending moment at point about point C? Bending moment at point, now find out the bending moment at point C is equals to, now find out the bending moment at point C. The RA reaction RA into perpendicular distance is L by 2. RA into perpendicular distance L by 2, which is equals to RA equals to W by 2 into length L by 2, that is W L by 2. This is the linear equation. Let me go back to sign convention for bending moment diagram. In this case, the sign convention for the bending moment diagram, if the shape of the bend, shape of the curvature is convexity, top fiber is convexity, then the moment is negative, and the shape of the curve is shape of the top fiber is concavity, then the bending moment is positive. So in the simply supported beam, if applied the load, it may be bent like this, that means concavity shape. So in this case the bending moment is positive, never negative. In this case bending moment is positive. Now how to find out the bending moment for the simply supported beam? First let me more concept for shear for sign convention for bending moment. If I divide it in both, if I choose a section, cut a section center, it is the right side portion and it is the left side portion. You can also note down the shear for one more point for shear for sign convention for bending moment. You can also note down for right side section, for right side section, for right side section, the clockwise moment, that means positive bending moment. For the left side section, anti-clockwise moment, that means positive bending moment. In the case of, if the load is upward direction, in the case of upward direction load, the reaction will be opposite. Now note down the one more concept for shear force for sign convention for bending moment. Taking the right side of the section, the moment of force taking the right side section, the moment of the force about moment of the force about the section if anti-clockwise 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 will be considered as will be considered as positive shear force, positive bending moment, positive bending moment, positive positive moment, bending moment, positive bending moment. If clockwise, if clockwise, if clockwise will be considered will be considered will be considered as negative bending moment, negative bending moment. Now taking the right side section, the moment of the force about the section if anti-clockwise, taking the right side section, this is the right side section, right side section, this is the right side section. The moment at point C is anti-clockwise, means positive bending moment, positive bending. If clockwise, then it will be negative moment. In here, in this case, it will be positive, it will be anti-clockwise, that means positive bending moment. Now similarly in the case of right side section, similarly in the case of right side section, in the right side section, sorry, in the left side section, this is the right side section, similarly right in the left side section, taking left side section, similarly taking left side section, left side section, left side section, the moment of force about the section if clockwise, the moment of force, the moment of force, the moment of force about the section if clockwise, clockwise, if clockwise, if clockwise will be considered, will be considered, will be considered as positive, as positive bending moment, positive bending moment. And if anti-clockwise, and if anti-clockwise, anti-clockwise will be considered, will be considered, will be considered as negative bending moment, negative bending moment will be considered as, will be considered as negative bending moment. Now look at the beam. In the left side portion, clockwise moment, if the moment of force is clockwise, the bending moment is positive. If the moment of force is anti-clockwise, for the left side section of the C, it will be negative bending moment. In this case, moment at point C for the from left side section, the reaction force is Ra is upward direction. That means the bending moment at point C, point C is anti-clockwise, clockwise. That means positive for the left side section. In case if I choose the right side section, the reaction force is upward direction. The moment at point C is anti-clockwise. That means positive bending moment. In both the cases, bending moment is positive because the bend of the curve is concavity. The shape of the curvature is concavity. Let me draw the bending moment diagram. Here I have to draw. Here let me draw the bending moment diagram. We also find out the moment moment about point A is 0, moment about point B is 0. At the both support, bending moment is 0. And point C is, we consider the left side section, the Ra into L by 2, reaction force into perpendicular distance L by 2, that means W into L by, W L by 4. W L by 4. The bending moment at point C is W L by 4. Let me draw the bending moment diagram. This is the beam. This point A, bending moment is 0. Point A, moment about point A is equals to 0. Moment about point B is equals to 0. Moment about point C is equals to WL by 2, which is positive upward. Moment about point C is equals to WL by 4. This is a linear equation, both sides linear. That means the shape of the bending moment diagram is a triangle shape. This is a positive bending moment. Bending moment diagram is like a triangle shape. I hope you understand. Now let me go for subjected to uniform distributed load. Uniform distributed load, simply supported beam subjected to uniform distributed load, W per unit length, entire the length of the beam, or this load is like a rectangle type of load, so W per unit length, This A, B, the center point, let me consider center point C. Now find out the reaction at point A, Ra, reaction at point B, Rb. Consider the moment about point, any of the point is 0, taking moment about, in this case moment about point A is equals to 0, moment about point B also 0 at a support. Let me consider taking moment about point, summation of moment about A or B. You can also consider summation of moment about point B. Let me consider a moment about point A is equals to 0, summation of moment about point A equals to 0. In this case, find out the moment about point A by reaction force at point B, Rb, and unit W per unit load, unit length, this uniform distributed by the this uniform distributed load. Now using Rb into total perpendicular distance is, let me, the perpendicular distance is L, total length of the beam is L. So moment about point A by Rb, which is anti-clockwise, say minus Rb into total length L plus uniform distributed load W, which is acting downward direction, the Rb reaction force is acting upward direction, this is downward direction positive, W into, this is clockwise, W into total length L into perpendicular distance, this is a rectangle type of load, perpendicular distance into L by 2 is equals to 0. This is the total moment about point A. For reaction force RB, the moment about point A is equal to RB into total length L, perpendicular distance L, and uniform distributed load, which is rectangle type of load, the area of the load entire the span is W into L at center into perpendicular distance from center to A, which is L by 2. This is the total moment about point A, which is equals to 0. Now find out the moment, now find out the reaction at point B. So reaction RB, which is equals to W into L by 2. Now find out the shear force and draw the shear force diagram. Shear force. Shear force at point A. Shear force at point A is equals to plus RA, positive reaction force, positive reaction at A. Now find out the shear force at point C. Shear force at point C is equals to RA, reaction force RA, minus the RA is equals to, find out the, let me find out the RA. This is the RB, reaction force RB is equals to WL by 2, and find out the RA. Now let me find out here, let me find out the RA. That means RA plus RB is equals to total load W into L, perpendicular distance L, W into L, because W is a uniform distributed load per unit length, so we have to multiply the length of the beam. Now RA equals to W into L minus RB equals to WL by 2, that is equals to WL by 2. So RA, shear force at point A, means RA, positive shear force, RA plus RA, that is WL by 2. Shear force at point C, upward force RA acting at point C always, and downward force, this is uniform distributed load from A to C, is W into total distance L by 2. This is RA equals to WL by 2 minus WL by 2, which is equals to 0. Shear force at point C is 0. The center of the beam is shear force is 0. Now shear force at point B. It is minus RB, reaction force always, equals to minus RB, which is equals to minus WL by 2. We can also find out the shear force at point B from this side. How to find out the shear force at point B? Let me find out the shear force at point B, this value. How it's come? The shear force at point B is equals to reaction force RA plus RA minus W into total distance. This is a uniform distributed load which is acting downward direction, that means negative. So this uniform distributed load into total length of the beam, that is W into L. RA equals to WL by 2, minus W into L, which is equals to minus WL by 2. Now draw the shear force diagram. This is the beam, this is point A. Shear force at point A is RA, which is equals to WL by 2, and shear force at point C is 0, and shear force at point B is equals to minus WL by 2, This is a linear equation. So you have to draw a linear. This is a positive shear force and this is negative. And this is the shear force diagram. Now find out the bending moment. This is a shear force diagram. Now find out the bending moment. Let me again draw the beam, simply supported beam of uniform distributed load W per unit length. Reaction W L by 2. Here also reaction W L by 2. This is A, this is B, this is the center C. And here to here this distance is L by 2. Now bending moment at point A. Bending moment at point A is equals to 0. Bending moment at point B equals to 0. Now only we have to find out the bending moment at point C. Bending moment at point C is equals to what? Bending moment at point C is equals to reaction force into perpendicular distance is L by 2. That is W into L, WL by 2 into perpendicular distance is L by 2 minus load, uniform distributed load up to point A to C is W into L by 2, W into L by 2, W into L by 2 into perpendicular distance from center to C, that is L by 4, which is equal to, this is the W L square by 4 is minus W L square by 8, which is equals to W L square by 8. Again, moment about point C by reaction force WL by 2 is equals to moment about point C is reaction force upward direction, that means positive, clockwise moment positive, and for this load, uniform distributed load up to here the load at point midpoint is W into L by 2 and perpendicular distance is L by 4, half of this length, perpendicular distance. Now draw the bending moment diagram. Now find out the bending moment at point B, how it's come 0. Bending moment at point B, moment about point B by this reaction force is positive, that means W into L by 2 into perpendicular distance is L minus uniform distributed load entire the span of the beam W into L into perpendicular distance from here to here center is L by 2, that is W L square by 2 minus W L square by 2, which is equals to 0. Now draw the bending moment diagram. I hope you understand. Now draw the bending moment diagram. It is also positive bending moment. It is the equation of parabola equation. This is a parabolic equation, parabola equation. The shape of the curve will be parabola. The bending moment at point A is equals to 0, moment about point A equals to 0, moment about point B equals to 0. Moment about point C is equals to what? Moment about point C is equals to WL square by 8. WL square by 8. This curve is a parabola. This is a parabolic curve. Positive bending moment. This is a bending moment diagram. Now let me go for a problem of simply supported beam subjected to difference load, point load and uniform distributed load, and solve and draw the bending moment diagram. Let me choose a problem of a simply supported beam subjected to different load. The question is, draw the bending shear force and bending moment diagram. Draw the shear force and bending moment diagram of the bending moment diagram for a simply supported beam simply supported beam as shown in figure. As shown in figure. The figure is given. The figure is point A. This is point B. This portion is uniform distributed load, and here also a point load. The uniform distributed load is 2000 Newton per meter and point load is 4000 Newton, and from this distance is 2 meter, and up to uniform distributed load this distance is 4 meter, and this is also 2 meter. Total span of the beam is 8 meter. So let me point is D point D, and this is point C. This is D and C. Now draw the shear force and bending moment diagram for this beam. Now we have to find out the reaction at point A and reaction at point B. Consider moment about point A is equals to 0, moment about point B equals to 0. Now taking moment about point A is 0. So sum of the moment about point, summation of all the moments of summation of the moment of all the force is 0 at point A. Now find out the moment about point A. Moment about point A for reaction RB into total perpendicular distance is 8. RB into 8, which is anti-clockwise, negative. And for this 4000 Newton load is bending moment at point A is 4000 into perpendicular distance 2 plus 4 plus 4000 into perpendicular distance is 2 plus 4, which is 6. And for this load, uniform distributed load 2000 Newton, total distance is 4 into perpendicular distance is 4 by 2, which is 2, 4 by 2. This is the total moment at point A, which is equals to 0. Now find out the RB, reaction B. So RB into 8 is equals to 6, 4 into 6, 24,000, and this is 8 into 2, 16,000, which is equals to 40,000. Now RB is equals to 40,000 divided by 8, which is equals to 5,000 upward direction. So RB equals to 5,000 Newton. RB equals to 5,000 Newton. Now find out the RA. Now RA plus RB is equals to total load are applied on the beam. Total load applied on the beam. The total load is, point load is 4,000. Point load is 4,000 and uniform distributed load is 2,000 plus 2,000. The uniform distributed load is applied up to 4 meter length of the span into 4. RA is equals to, this is 8,000, 8 into 8 plus 4, 12,000. 12,000 minus RB. RB is equals to 5,000, which is equals to 7,000. 7,000 Newton. It is also upward direction. So RA is equals to 7,000 Newton. Now find out the shear force diagram. Shear force. Let me again draw the beam. This is the reaction force at point B is equals to 5,000 Newton, and reaction force at point A is equals to 7,000 Newton, and uniform distributed load from A to D, this A, this D is 2,000 Newton per meter, and point load at point C is 4,000 Newton. This distance is 2 meter. It is also 2 meter, and it is 4 meter. Now shear force, find out the shear force. Shear force at point A, is equals to reaction force at point A plus positive reaction force at positive, this is 7,000 Newton. Now shear force at point D, find out the shear force at point D. For this uniform distributed load, shear force will be linear shape. The shear force at point D is equals to shear force at point A 7,000 minus uniform distributed load 2,000 into up to 4 meter length into 4. So minus 1,000 Newton. Now find out the shear force at point C. This is point C. Shear force at point C. What will be the shear force at point C? shear force at point C will be what? Shear force at point D. Shear force at point D, shear force at point D minus downward force is 4000, which is equals to minus 1000 minus 4000 is equals to minus 5000 Newton. And shear force at point B, shear force at point B, shear force at point B is equals to reaction force always minus, that is minus, it is that is also shear force at point C. Here no load, this is also reaction force. That means the shear force at point, there is no force at point B, so the shear force at point B is equal to shear force at point C. That means minus 5000 Newton. That is reaction force. I already say that for sign convention, for shear force the shear force, for the right side section is always negative. The shear force at point B is minus reaction force at point B, that is minus 5000 Newton. Now draw the shear force diagram, how it's look like. Let me draw a beam. This is the beam, this is point A, and this is point B, this is point C, and this is point D. This is point C. Shear force at point A is 7000 Newton, which is positive. This is 7000 Newton. For uniform distribution load, the shape of the shear force diagram will be linear. Now shear force at point D is minus 1000. Say this is 1000. Let me it is this 7000. This is 7000, and this is 1000. Shear force at point. Let me draw the linear from here to here, and shear force at point C is minus 5000. This is a 5000 minus. In at point C, point load, that means we'll get two shear force at just to left and just to right. It is the just to right. Now just to left, it is just to right. Now just to left, what will be the shear force at point C? Just to left. Just to left, that means shear force at point D. Shear force at point D, which is equals to minus 1000 Newton. Always the shear force at point C just to left, just to left is minus 1000, and shear force at point C just to right is 5000. That is 1000, and this is 5000. And shear force at point D is 1000 Newton minus, it is also minus, and this is a 7000 plus, and shear force at point B is always minus 5000. This is also minus 5000 Newton. This is the positive shear force. and this negative shear force, this portion are totally negative shear force. This shear force diagram for simply supported beams subjected to different type of load. One is uniform distributed load up to 4 meter length, that is 2000 Newton, and a point load at point C is 4000 Newton. The shape of the shear force diagram of this beam is like this. The always shear force shape of the shear force always linear for the uniform distributed load, and for the point load is also always constant. Now find out the bending moment diagram for this beam. Let me again draw the beam. This point B is 5000 Newton, and this is point A, 7000 Newton. This is point D. A to D is uniform distributed load, that is 4000 Newton per meter, 2000 Newton per meter, and point load at point load is 4000 Newton. This is 2 meter. This is also 2 meter, and this is 4 meter. Now find out the bending moment and draw the bending moment diagram. Bending moment. Bending moment about point A is equals to 0. Previously I have said the bending moment at point A equals to 0, bending moment at point B equals to 0. Now bending moment at point D, this is the C. Bending moment at point, find out the bending moment at point D. Moment at point D is equals to moment at point D by reaction force is 7000 into perpendicular distance is 4 meter. So 7000 into 4 meter distance of length 4 meter minus 2000 Newton uniform distributed load acting downward, 2000 distributed load into 4 meter length into perpendicular distance is 4 by 2, that is 2. This is the bending moment at point D, which is equals to 28,000 minus 16,000 is equals to what? 12,000. 12,000 unit is Newton meter. This is the parabolic shape, the parabolic equation, like parabolic equation. Now find out the bending moment at point C. Bending moment at point C is equals to 7000 into perpendicular distance 4 plus 2, that is 6. Let me write 4 plus 2 in this form. 4 plus 2 moment about point C for this load 7000 into 4 plus 2, and for uniform distributed load 2000 uniform distributed up to what? Up to 4 meter length into 4 into perpendicular distance 4 by 2 from here to here, from center of the uniform distributed load to point C, that means 4 by 2 plus from D to C is 2, that is equals to 4 plus 2 6, that is 42 1000 minus 2 plus 2 4 16 32 32 32,000 which is equals to 10,000 Newton meter. Now bending moment at point B. At point B is 0. Let me how it comes 0. Let me check. It is 0 or some value. Bending moment at point B. The bending moment at point B, which is equals to 7,000 into total length perpendicular distance, 7,000 into perpendicular distance 4 plus 2 plus 2, 4 plus 2 plus 2 plus for uniform distributed load 2000 up to 4 meter length into 4 and perpendicular distance 4 by 2 plus 2 also plus 2 plus for this point load 4000 into perpendicular distance is 2 meter. For 8 56,000 plus 6 into 4. Let me calculate it. 2000 into 6 into 4. 6 into 4 which is equal to 48,000. Sorry, this is minus. I'm really sorry. This is minus 48,000 minus 8,000. 4 into 2, 4,000 into 2, this is 8,000, which is equals to 48 plus 8, 56,000 and this 56,000. That means 0. Bending moment at point B is 0. Now draw the bending moment diagram. This is beam. Bending moment at point A is equals to 0. Moment at point A equals to 0. It's point A. Moment at point D is equals to what? Moment at point D is equals to 12,000 Newton. Moment at point D equals to 12,000 Newton. Moment at point C is equals to this is the point D, this is point C. Moment at point C is equal to 10,000 Newton. 10,000, here the 10,000 Newton. Moment at point C equals to 10,000 Newton. And moment at point B equals to 0. The shape of the bending moment from A to D is parabola, because uniform distributed load, this parabolic equation, this is the parabolic equation, like so it will be, its shape will be parabola. From D to C is point load, that means linear up to B. This is the linear shape up to B. I'm really sorry. This is the this is the shape of bending moment diagram. This totally positive bending moment. Totally positive bending moment. Bending moment diagram. I hope you understand. Let me some brief review for the bending moment diagram for the simply supported beam. Bending moment, the bending moment at point A is 0, bending moment at point also B is 0. For the simply supported beam, both support point bending moment is 0. The moment about point D is 7000 is upward, that is clockwise bending moment, clockwise moment which is positive, and for the uniform distributed load is anti-clockwise which is negative. So 7000 into 4 meter length, 7000 into 4 meter minus 2000 Newton uniform distributed load up to 4 meter length, 2000 into 4, this is a load into perpendicular distance from center to CG distance, perpendicular CG distance, which is 4 by 2. So total bending moment at point D is 12,000 Newton, which is parabolic equation curve. For bending moment at point C, bending moment point C is also 7000 into total perpendicular distance 4 plus 2, which is 6, minus 2000 Newton uniform distributed load up to 4 meter length, and perpendicular distance 4 by 2, half from half of the uniform distributed load, half portion of the uniform distributed load to C, that is 4 by 2 plus 2, which is 10,000 Newton, and the bending moment at point B is 0. So this is the bending moment diagram for the simply supported beam. I hope you understand, you enjoy the lecture. Thank you so much.